Hello, welcome to this lesson on Brønsted-Lowry acids, bases and pH. So in this recording we are going to look through Brønsted-Lowry acids and bases, the definition for acids and bases, and also to identify the conjugate acids and base pairs. So this is something that we're going to really start off with, and also brief look at the definition for acids and bases, and look through how to calculate pH from concentration of hydrogen ions in solution. We're going to be looking through acids, and in this we are looking first we look first of all how to calculate pH of weak acids and then strong acids. Okay, we're going to start off with strong acids. Weak acids is slightly the next thing we're going to do, and then bases we're only going to look at calculating pH of strong bases. Okay, and that's what is in the UK specification for OCR. Okay, so that's what we're going to focus on. Many thanks to Lee Francis. I say this because I'm using his amazing resources that he shared through TES, just Times Educational Supplement. Okay, thank you. We are going to recall and use this expression for pH. pH is calculated once you know this hydrogen ion concentration. This expression, the square bracket, as you probably know, is the concentration of what's inside, right? This time it's the hydrogen ion concentration, and if you take the negative log of the hydrogen ion concentration, you get the pH. And as you probably know, it ranges from 0 to 14. That is the pH range, and that is the whole number that you get from the hydrogen ion concentration. This function is the reverse of what you see here. You know, if you get pH from the hydrogen ion concentration, you can do the reverse. You can get the hydrogen ion concentration from the pH by doing this 10 to the power negative of the pH. Okay, so these two we're going to be using in this tutorial. Arrhenius theory, we start off with that. Although this is not very often tested, it's a good starting point. It's a definition for acid according to Arrhenius is that anything that produces hydrogen ions in solution in water. So we're talking about protons, sometimes referred to as protons, H plus ions, right? If you produce H plus ions in if a substance produces H plus ions in water, that's acid according to Arrhenius. Base is something that produces OH minus ions, so that's a good place to start. Brønsted-Lowry definition of acid is pretty much the same. It produces H plus ions. This should be a subscript, so I'm going to rewrite that as H plus ions, not like that. Okay, so H plus ions, if that produces, we call that as an acid. That's Brønsted-Lowry definition of acid, right? Base is something that accepts, so you can see the slight difference there. You see base is something that produces OH only. That's also true, but base is anything that can accept a proton, which is a better definition for a base, because that includes something like NH3. NH3 can accept a proton, although it also produces OH minus ions. So it's a definition that will include substances that cannot be otherwise defined as a base. So you need to know the definition for acids and bases, Brønsted-Lowry theory, the Brønsted-Lowry definition for an acid. Okay, strong acids. So recall, strong acids, they completely dissociate, completely ionize. Weak acid only partially dissociates. So example of a weak acid is ethanoic acid, right? So this dissociates, and normally we use equilibrium symbol CH3COO minus, and this is called the conjugate base of the acid. So that's the acid, this is the conjugate base of the acid, and plus the H plus proton ion, right? So all of these are in aqueous conditions, water. Okay, right? And then you have think about a strong acid like Cl. You use a single arrow, forward arrow, not this reversible symbol here. Use a single arrow and then you put H plus, the proton, and the conjugate base, and that's aqueous. Okay, so this is completely ionized. That's why we call them as strong acids. Okay, don't confuse this with concentration. When we say concentration, it's about how many moles are present in a liter. Okay, so that's a different thing. Okay, first objective is to be able to identify the acid and its conjugate base. Okay, now that is a strong acid that reacts with water. That proton gets transferred to the water. Okay, so we identify the acid first. I'm going to remove these labels. We have to identify in a specific way, in a number system, right? So once you identify who's transferring the proton, the species that transfers the proton is this one, so we label that as acid 1. And this is a useful sequence to follow. So as soon as you label acid 1, you go to the other side. On each side you have an acid and a base, so if you can keep that in mind, all you have to do is look for the conjugate of that, which is this Cl minus, and label that as base 1. Okay, this is to just identify these two as a pair, right? A conjugate acid base pair. Okay, so that's that. Now keep on the right hand side. Now you got a base here. This has to be an acid, right? Because on each side you have an acid and a base. Now that you have an acid 1 already, so this has to be an acid 2. Okay, why? Because that can actually donate a proton back to this base, and that reaction can be reversed to produce the HCl. Okay, so this can donate a proton back to the conjugate base and produce that HCl. That's why that's an acid now. It can donate a proton. So the only thing that's left now is the base 2. So this way of labeling is really essential. You should be able to do this. So you start off with labeling, first finding out who's transferring, which species transfers the proton, label that as acid 1, go to the other side, the product side, label the conjugate of that as base 1, and then acid 2, and then base 2. Okay, a little bit more practice from my side. I'm going to just tell you how this works. Now, if you want to try this out, pause the video now, and you can actually have a go before you check, and then you can come back and start checking the answers, right? Okay, so that's ethanoic acid, right? That is the conjugate base. You can see that is transferred, that proton, to the water. Okay, there, easy to identify that as acid 1. Now look for the conjugate base over here, so that's base 1. Once you've done that, this has to be acid 2, because on the product side you're looking for an acid and a base, so this has to be acid 2. You already have acid 1 here, so this must be acid 2. Now that means you have just base 2 left. So we've done base 1, so this must be the base 2, right? Again, we do this to identify the pairs, right? So nitric acid, again, you can pause the video, try, and then check. I'm going to go ahead and actually do this now, so you can check this, check your thinking if that matches, right? So nitric acid has donated the proton to this. This is a strong acid, that's a weak acid. Both do the same thing. They transfer a proton. They produce a proton in H plus hydrogen ion in aqueous solutions. So that is acid 1, and this is its conjugate base. I'm going to label that as base 1. Now that has to be acid 2, and that is base 2, right? So that way of numbering, again, we do this to identify the conjugate acid base pairs, right? So keep that in mind. Okay, now here you can see ammonia is actually accepting the proton from here. So in this case, the water is acting as the acid, right? Because that is transferring the proton. So we label this as acid 1. At any stage, stop the video, pause the video, and then you can actually try and then check if you got it right. Okay, so acid 1. So then I look for the conjugate of this, which is OH minus 1, label that as base 1. This has to be acid 2. Now it's got this proton, it can actually transfer it back to the conjugate base. Now you got acid 2, so that means this has to be base 2. Okay, so this is something for you to practice. Okay, so you can identify acid 1 and acid base pairs like we just discussed, and then come back and continue playing the video and check your answers, right? This before you go away, like you can have a look at this. This looks bit strange, but this is the ethanoic acid that you're familiar with, right? All A-level students should be familiar with ethanoic acid, and if just written it in a different way, but you can see that this has lost that proton and you're left with what's left, right? So this is the same as CH3COO. Now you can pause the video and try this for yourself. Check your answers. I hope you got all of them right. Pause the video, check. Now that we have identified the conjugate acid base pairs, before we progress on to calculating pH, we need to have some basics done. Okay, an acid, a weak acid, so we are looking at weak acids first to start with. It actually dissociates like so, right? So we need to know this before we look at acids, both strong and weak. It combines with water to produce this, right? HA is a general form of writing an acid. Okay, HA represents an acid, and as you can see, that's a conjugate base of this. We should be familiar with that equilibrium Ka, equilibrium constant Ka, and that is the product over this, right? The water is not often included, right? So when you write an equilibrium constant for this, I'm going to write this in a simpler way, like HA producing H plus, same thing. So I'm going to write in the same format, A minus for this, and then plus H plus. Okay, these two are the dissociation product. Obviously this is an aqueous solution. I'm not going to write that every time. No, right. So if I write the Ka now, it looks much simpler. So you got the A minus concentration, and then you got the H plus. Instead of H3O, I just write H plus, and then divide that by the undissociated acid HA, right? Okay, now things to notice. I have just left the H2O out. That's because the concentration of H2O it does not change as much. If you look at any solution, the concentration of water is pretty much the constant, because the whole of the solution, say for example you're putting some acid in here, the concentration of the acid is so small, the rest of it is just water, right? So the concentration of water does not change. I can actually show you, say consider 200 centimeter cube. You can actually consider any volume and work out the concentration of water. You can pretty much see that it is actually the same number every time. So I'll explain why this is significant later on when we look at Kw, right? So if you look at the we're trying to understand why water concentration is not there in the denominator, right? So we only got the HA. So that is 200 centimeter cube, and as you know, the density of water is 1, so this is like 200 grams. Now if you convert that to moles of water, so we're going to assume the whole of that is water pretty much. Okay, so there's a small amount of mass of acid present there. Okay, we're going to assume, okay, so 190 grams of water or something, right? So instead of that, I'm approximating here 200 grams of water. Divide that by 18 to find the moles of water. Okay, N of H2O, that gives us 11.1 moles of water present in 200. You can do any volume and it gives the same answer, right? Then you divide by the volume. We want to work out the concentration of water, right? So you divide C equals N over V. Now we have 11.1 moles. N represents moles, V for volume in liters, right? Now we use 200 centimeter cube, right? So that is in liters, 0.2. Now that gives us 55.1, 55.5 mole per dm cube. Now you can do for any volume, the water concentration is that. So that is something that you have to remember. We'll have to come back to that later on. That's why you don't include water concentration when you write the Ka for a weak acid. Okay. Now we're going into pH, use of that expression, minus log of hydrogen ion concentration. So your goal for working out pH is whether it's strong acid, weak acid, strong base, you just need the hydrogen ion concentration. Okay, without that you can't work out pH. Next we need to understand how to use this expression. The formula for pH to calculate pH is minus log of H plus ion concentration. So that square bracket is concentration of H plus ion, right? And this is the inverse of it. From the pH you can also calculate the concentration of H plus ions. Let's have a look at this. Say for example you have a pH of 9.14, and then we want to know to find the H plus ion concentration. All you have to do is 10 to the power minus 9.14. So you get the answer. So you do hydrogen ion concentration 10 to the power minus whatever the pH is. That gives us 7.24 times 10 power minus 10. Put that to 3 significant figures to match that. Mole per dm cube. Don't forget the unit because you're working out the concentration. So to summarize, if you want to do find pH, you need the hydrogen ion concentration, and you can actually get hydrogen ion concentration by knowing the pH. So let's actually do that. What you need is, you got the pH, so all you have to do is this to get the hydrogen ion concentration. So let's do 10 to the power minus 9.14, and that gives you the answer. So there, 7.24 times 10 power minus 10. Don't forget the units for concentration, mole per dm cube, right? Okay. So if we have this hydrogen ion concentration of 2.3 times 10 power minus 5, this m means mole per dm cube, right? So the capital M is a short form of writing that. Okay, so now from this you can actually work out pH equals minus log of that number, that concentration, and that gives you the answer, right? Okay, so that will be that. Okay, so these two are really basic functions and formula or expressions to calculate pH, and from the pH you can calculate H plus ions, and you should be really familiar with this to go ahead and do the acids, the strong acids and weak acids, calculating the pH. Okay, just a reminder about, there are 3 types of acids. You're going to need to use this idea that produces 1 H plus ion. This acid produces 2 times H plus ion. That's why we call them dibasic. Monobasic acid. Then you have tribasic acid producing 3 H plus ions for every mole of this, right? So 1 mole of this will produce 3 moles of this. 1 mole of this produces 2 moles of H plus ions. 1 mole of HCl produces 1 mole of H plus ions. That monobasic, right? Okay, so keep that in mind. We are going to be looking through this, not these reactions for the moment. We're really focused on the pH and the calculations of pH for strong acids and weak acids. For strong acids, calculating pH is really straightforward. All you need to look out for is, do we have the concentration of the acid? So once you have the concentration of a strong acid such as hydrochloric acid, nitric acid, and sulfuric acid, and so on, right? So once you got this, if you have the concentration of the strong acid, you have the concentration of H plus. You know why that is? Because this completely dissociates. Say for example, HCl completely ionizes into into the ions once it is in solution, right? Once in water, it completely ionizes, right? So the number of moles of HCl is going to be equal to the number of moles of this and the number of moles of that, right? So all you need is the concentration of the acid. So you got 3 moles 1500 centimeter cube. Converting that to concentration, moles divided by volume in liters. So I'm going to write that in liters, 1.5, and if you calculate that, that gives us 0.2 moles per dm cube, 0.2 mole per dm cube. That's the concentration of the acid, and that is the concentration of H plus ions as well, just to remind you of that, right? So this is also the same, mole per dm cube. So calculating the pH for concentrated acids is really straightforward. So you have the concentration of the hydrogen ions. All you have to do is put that in our expression for pH minus, so pH would be equal to minus log of this 0.2. that gives us, it says 0.77. That's it. pH hasn't got any unit. So that's how it is. Strong acids, all you have to do is work out the concentration of the acid itself. Even if you're given it straight away, that is the concentration of the H plus ion. Do that expression, done. Okay, so 1 mark question, that is, right? Okay, here is a question where you have to use different functions that we looked at so far, different expressions. Okay, so we are given 10 centimeter cube of a pH 4, and this is diluted up to a volume of 200 centimeter cube, right? So we take 10 centimeter cube of pH this. Okay, so all you have to do is follow these steps. You have to have the original concentration, then the dilution factor, work out the new concentration, and then the new pH. Okay, so to work out the original concentration, as you already know, so you've been only given the pH, so the concentration would be 10 to the power minus 4. That gives us the concentration. So there, so you have the concentration written like so, right? 1 times 10 power minus 4 dm mole per dm cube. Now you look at the dilution factor, the original volume divided by the final volume. So 10 divided by 200. Okay, so 10 divided by 200, that gives you 0.05. Now you work out the new concentration by actually multiplying the original concentration by this dilution factor times 0.05. That gives us the new concentration of the hydrogen. So we have this, multiply by that, that gives you 5 times 10 power minus 6. Now to work out the pH, minus log of this concentration, 5 times 10 power minus 6. That should give us, that gives us 5.30. Always keep the pH answers to 2 decimal places, unless the question asks you to give it to different number of significant figures. Okay, when you these are practice questions. When you see mild, that means it's slightly easier. So mild for slightly easier, warm for slightly harder, and then hot, really hard. Okay, but you can practice. If you're revising for the final exam, choose 1 or 2 just to refresh your memory on this and make sure that you're really fast with the calculator. Otherwise, you can skip. If you're really confident, super confident, skip this. But for now, pause this, practice, and then check the answer. I hope you've stopped and now you're checking the answers are here, right? Okay. These are slightly harder questions, right? I just want to remind you of certain things before you actually go ahead and do this. Now you are given this many moles per liter, so you are given the concentration of the acid. Mind you, you need the concentration of H plus ions. So the concentration of H plus ions from this would be 2 times the concentration of this, right? Because sulfuric acid being dibasic. Remember that, yeah? There as well again. When you go the reverse, you're going to work out the concentration of sulfuric acid. Just do the reverse of that. Just be careful with that, right? So from the pH, you will be working out the concentration of H plus ion, right? Now the concentration of H plus ion would be twice as much this, because 1 mole of this would produce this. So once you have the concentration of this, you just have to divide that by 2 to get the concentration of the acid. So now you can pause the video, try these practice questions, and then you can check the answers. Check the answers. I hope you got all of them right. As I said to you, you can pick and choose what you want to do. Like if you're really confident with this type of questions, you can skip this and go to the hot ones. Hot questions are here, right? Slightly harder questions which involves dilution, right? I want to tell you another little trick that you can do. Sometimes you don't know which way to divide the original volume by the final volume or the final volume by the original volume. To avoid that confusion, there is another way to work out a new concentration when dilution is involved. So you have 100 centimeter cube of this concentration, right? So you can write, if you're just interested in the final concentration, this is what you can do. So let's pick this one right here, which involves dilution here. So 0.1 is the volume, and I put the concentration 0.2. That's the original concentration. Now made up to 500. So I have the volume here, but I do not have the concentration, right? So I put C here. In other words, this is the formula for concentration and volume changes when there's dilution involved. C1 V1 equals C2 V2. That's the original concentration, original volume. Concentration after dilution, that's the volume or the final volume of dilution. Okay, the final volume, in other words, right? So here is 0.1. That's our volume converted to liters, and that's 2 moles. So I put 0.2 here. Okay, it's 2 moles here, 2 mole per dm cube. So I'm going to rewrite that here. 0.1 times 2 equals, then you have 0.5 as the final volume, and we don't know the concentration of this. So C2 is something I don't know. And you just divide both sides by 0.5, then you get the final concentration. That's another way of remembering without dilution factor, and if you're getting confused with that, right? Okay, so here you have to convert gram per dm cube into mole per dm cube. I hope you can do that. You just have to find the formula mass of hydrogen chloride, divide 10 by that, and then once you convert the gram to dm to moles, you get mole per dm cube, right? So you just have to divide that by the formula mass mR of HCl. That gives you, that will convert the gram to mole, and then you have the concentration of HCl. Both of these are strong acids, so it should be really straightforward to work out the pH. Now you can actually pause, try these questions, choose what you want to do, and then check the answers, right? Practicing more questions will make you faster in the exam. There you can check the answers. I'm sure you got all of them correct. Okay, these are all easy questions. Okay, later on, once we've finished all this, we're going to go through some exam questions. Okay, so we'll look at a variety of exam questions in part 3. So this is part 1, second part is buffer, and then part 3, right? Here is more answers for the hot practice questions. Moving on with the strong and weak acids. Okay, we're now moving on from strong acids to weak acids. Mind you, strong acids completely ionizes, weak acids only partially ionized. So you can see the red circles are the H plus ions. You can see the weak acids are together. Only some of them have split into the blue and the red bits, and that red bit is the H plus ions, right? So this weak acids partially ionizes. Keep that in mind. And also our expression for Ka, we're going to be using that. Ka is the acid equilibrium constant. It's just like Kc, like I said before. And now the water concentration has been multiplied into the Kc. That is now become Ka, special for acids, right? So just to remind you, for a weak acid you have this, right? H plus plus A minus if you ignore the water there, right? Okay, H plus A minus divided by HA. Now the HA stands for a weak acid. That is now Ka, right? So let me just write Ka here. Okay, this is an approximation. When we write like this for a weak acid, we consider the HA at equilibrium. This is the equilibrium concentration of HA, right? So what about there's going to be some of the acid dissociating, right? So the equilibrium, if you're starting off with a certain number of moles of HA, at equilibrium you're going to have slightly less, right? But then we're going to assume that's going to be really minuscule difference between the very small difference from the start concentration of this and the equilibrium concentration. So a small fraction of the molecules of HA will actually dissociate like this, right, and ionize like this. So we're going to consider the equilibrium concentration of HA is the starting concentration of HA, which is an approximation. And then the change in this, that's one thing. Okay, dissociation forms equal amounts of H and A minus. Okay, so if one of this splits, you're going to have one each of this, right? So we're going to have the same number of H plus ions and A minus ions. Is the second approximation. Okay, right? So if you consider the original equation, so Ka equals H plus A minus, which is the conjugate base of the acid, and then HA, the concentration of the acid itself. Now if this is the same as that one, this has been replaced by H plus. Okay, so you can because these two have the same value, so I can write just H plus. Why we're writing H plus and not A minus? We are interested to calculate H plus, right? For pH we need H plus, so replacing A minus with H plus, we need an expression for H plus. Now this becomes H plus square divided by this Ka. Now if you rearrange this, that comes over here, so so H plus square equals Ka times the weak acid concentration, right? Now if you want H plus on its own, you just do square root of this side HA. The whole thing should be taken a root of, and that's what you see here, right? And so that's the expression we need to know. Because we now got the H plus ion, we can actually work out pH by doing minus log of the hydrogen ion concentration. So that's the method for weak acid. There are variations in the type of questions that you get. We are looking at just revising the fundamentals, going through them, and then we look at slightly harder questions, right? So make sure that we're really strong with the basics. Okay, so let's practice this. I'm going to show you how to do this, and then you can practice on your own independently. So here phenol is a weak acid. Another way of identifying something is a weak acid is if a Ka value is given. If the Ka value is low, if the Ka value is given at all, then you're looking at a weak acid, right? The Ka value for strong acids is really high. Okay, so this is 10 to the power minus 2, minus 3, minus 4, up to 10 power minus 10, and even low, smaller, then you're looking at weak acids, right? So phenol is a weak acid, that's a Ka value. First of all, right, we are working for a pH, right? We need the pH, right? So first start with the expression for Ka. If you are short of time, you can actually go straight to that expression that we just looked at here. Okay, that expression. Okay, so I'm just going for one last time with the expression, otherwise you can just go straight with that expression of calculating this, right? H square. So now H square would be equals Ka times the concentration of the weak acid. Now if you want H plus, then square root of Ka, you can straight away use this expression. No need to actually show this each time. Okay, so if you're working out one more question, then you can actually straight away do this. So calculate H plus, we've done that here, so I'm going to rewrite that expression here because that's gone a bit messy there. Okay, so HA There I have just put the expression and substituted Ka from what's given here into that, and then the concentration of the phenols given there, so I put that here, concentration of the acid. And now all you have to do is simplify and find the value for this expression. So I'm getting 5.8. Obviously you can check this, 5.8. I'm going for 2 decimal places. Okay, 2 decimal places. Okay, so that's how you do for week. That is a basic calculation that we all have to be able to do. Right, so let's practice that, and if you are really confident, you can pause this now and actually try this out, check the answer in a minute. I'm going to go straight through to actually showing you how to do this. Later on you're going to have plenty of practice with this, right? So for now you're given Ka value of nitrous acid, not nitric acid. This is a weak acid. You can make out from the value of Ka, and you got 2m solution. This m actually means mole per dm cubed, right? So you are given the concentration of a weak acid, right? So you want the hydrogen ion concentration equals square root of Ka times the actual concentration of the acid itself, which is let me write the expression first. Okay, HNO2. Then you have the values substituted in there, 4.5 times 10 power minus 4 times the concentration of this, just 2, and that gives the concentration of H plus ions. I get 0.03, and then if you do that's the concentration of the H plus ions, mole per dm cube, right? And then you do the next step is to work out the pH, minus log of the hydrogen ion concentration. So I'm going to put 0.03, that gives me 1.52. Here's another example. So you can now go ahead and practice these things. Okay, here's the first easy questions, mild. They can pause the video and actually practice this. So it's all straightforward questions. So you got pKa value given. I haven't mentioned about pKa value, right? So how do you get calculate pKa value from Ka, right? What's the connection between that and this? For now, this is enough. If you do minus log of Ka, you get pKa, right? Okay, for now that's enough. We'll later on look at the connection between Ka and pKa. Briefly now, Ka value, if it is larger, pKa value will be smaller. Okay, so as you can see here, the difference between this and this is a smaller Ka value, and that should be giving a higher pKa value from that. So you can actually calculate this from here, right? You can actually work out the expression for these and then calculate Ka from these Ka values. Doesn't make any sense. All right, so just do this one. Okay, calculate pKa from these Ka values, right? I get it. Okay, so this is calculate the pKa from this Ka from the pKa values, because this is just the reverse of this. Okay, so this is pKa value, right? So you can practice these questions and then check the answer in a minute. So pause. I hope you're checking the answer now. Ka from pKa, pKa from Ka, right? So check the answers, see if you're getting this right. Okay, the purpose of pH, if you've been wondering, it is to actually reduce the number to a manageable size, because the concentration numbers are often very dilute, 10 to the power minus 8, minus 3. So the pH actually gives a nice way of, an easy way of comparing the hydrogen ion concentration of different solutions. They're slightly harder questions, right? So here, butanoic acid, methanoic acid, all of these are weak acids. Ka values are given, and there's pKa value is given. I hope you can actually work out the Ka from this. because that's what you're going to need to work out the pH, right? So if pKa is given, Ka would be 10 to the power minus 4.2, right? Pause, do these questions, and then check your answers. Again, you have to pause because this keeps moving. Now, hot questions you can actually see. Let me see before I hand over to you. One moment. Let's see if there is anything that needs explaining. Actually, no. You can actually do all of this. To work out stronger acid, you can compare Ka values or pKa values. You can actually convert these to Ka values and compare to see which one is bigger. The bigger Ka value, the stronger the acid is, right? Because you have more ions of more H plus ion produced, right? So I would expect this being a bigger pKa value, giving a smaller Ka value, a weaker acid, right? You can now go ahead and do all of this to check, and then check your answers. There, hope you got all of them right. Pause as I'm going to keep moving. Okay, so these are the limitations of Ka value calculations, problems in using the Ka expression, right? So the pH value that you calculate using Ka expression of anything more than 6, that's really weak acid, right? More than 6 and up to anything more than 6, then the water dissociation. Water also produces some H plus ion, and this is not going to be the same because you have other ions in the solution, right? So H plus ion is going to be produced by the water, and that becomes significant. So far it's very small concentration compared to the acid, so we keep ignoring. Now we're looking at really weak acids, really weak, where the hydrogen ion concentration is already really small. So for very weak acids, there is a problem. Because it doesn't give you very accurate concentrations of or idea of the concentration of H plus. Okay, so that's one problem. Doesn't work for stronger weak acids when Ka is more than 0.02, right? So why is that? Because you are assuming the Ha at the start, whatever concentration you're starting off with is going to be the equilibrium concentration. This is not true if the weak acid that you're saying weak is a stronger weak acid, where the dissociation is considerable, where the Ka value is more than 10 power minus 2, which means you have lots of H plus ions, right? So this means a more higher proportion of the Ha ions dissociated already, so that means it's not a good approximation. So that's a limitation of using Ka for calculation of pH. Here is a variation of what we've been looking at. So here you're asked to determine the Ka, right, for this. So just write the expression for Ka. We're saying propanoic formic acid, right? Formic acid is this HCOOH, but what we're going to do is just like put a H or usual expression, a simplified way of writing this, right? Because we only need to know the Ka, right, divided by this Ha, right? And remember, for weak acids these two are the same, so it can be written as H plus square divided by Ha. So now think about, what do I have here to work out Ka? We need H plus ion. Do we have that? It's not directly given, the form of pH, so you do H plus ion concentration equals 10 to the power minus 2.04, and then you have to do is substitute it over here. One thing missing in this is the concentration of the weak acid. Okay, it's not given in the problem. I think got missed in the pasting onto this this page. Okay, so we're going to have the concentration given to us. that is 4.91. Okay, so the concentration of this acid, concentration 4.91 mole per dm cube, right? So you just have to substitute that over here. Okay, right, the concentration, I made a mistake, is 4.91. It's actually 0.491. so you have the Ka value. This is the hydrogen ion concentration that you work out with this, with the pH value 10 to the power minus 2.04. Once you got the pH, the hydrogen ion concentration, that goes in here at the top, square that, divided by the concentration of the weak acid, which is here 0.491, and that gives you the Ka value. Remember, the unit for this is here. There is two concentration units here, so if I write the units for H plus, that will go as this, mole per dm cube to the squared, okay, divided by, you have mole per dm cube, right? So if I cancel one of them out for this, you're left with just mole per dm cube, right? So mole per dm cube is the unit for Ka in this, okay? Another important idea to understand is ionic product of water. It is a constant number, so when water itself is can ionize like so, H plus and OH minus ion. So in pure water you have equal amounts of this and that, so you have a pH of 7. So we'll see how that is, right? We can write an equilibrium constant for even this ionization, and that is given a special symbol of Kw. I'll explain how that is. So initially you write Ka assuming water as acid as well as alkali. It's amphoteric, which means it can act as acid as well as alkali. So you can see water can accept a proton as well as give a proton. So when one H2O molecule transfers a proton, that becomes H3O, and that is the conjugate base, OH minus ion, right? So if you write the expression, this is not very clear, so I'm going to write that over here. Ka equals H plus and OH minus divided by H2O, that's a liquid, aqueous, right? Aqueous, right? Okay, so that's the expression for Ka for water, right? Now we know the Ka, the water concentration is pretty much the same, and here we are looking at just water on its own, right? So whatever the water that's left, that's the concentration is constant, 55.5, something like that, right? So if you multiply that by, so this is going to be a constant number, you multiply on both sides by the same value, 55.5 something, you can actually change the Ka into something else called Kw, right? So this, the product of these two is going to be a constant, is now going to be called as Kw, which is a product, ionic product of H plus and OH minus ions that's present in water, okay? Also, it's a fact that even whether you have acids or alkali in solution, the product of the H plus and OH is always a constant, which is 1 times 10 power minus 14. Okay, so this now is mole square dm to the power minus 6. Why? You're multiplying two concentration units. Okay, more on Kw value. So we now have from Ka, because we multiply by that constant of water concentration, now we have Kw, the ionic product of water, or the value of Kw for pure water is pH of pH 7. So how is that pH 7? Let's have a look. The concentration of the product is 10 power minus 14, which means the hydrogen ion concentration is going to be the square root of this. Okay, this is a subscript, so I'm going to rewrite that here. So H plus ion concentration is going to be now like so. Okay, so that's what it is. and that gives us this value over here. If you take the square root of that, that gives you this, and then you got the hydrogen ion concentration. All you have to do, so you're working out the pH of just pure water. Okay, just do minus log of the hydrogen ion concentration, you get 7. Now you know why neutral pure water has got a pH of 7, right? Now this is an important idea we're going to use for calculations, so make sure that you remember this, right? Because to work out the pH of bases, we need this idea. Okay, so to work out pH of strong bases, so we're only looking at strong bases. So looking at something like sodium hydroxide, this completely ionizes, as against weak bases like ammonia only partially ionizes, hence you got this equilibrium appearing in that equation, right? The symbol for equilibrium is the reversible reaction. That means the reaction is reversible, right? The monobasic monoacidic bases release 1 mole of OH, so keep that in mind. It's just like the monobasic acid, you got monoacidic bases, just the reverse of it. If you got 1 mole of OH per molecule, then you have monobasic. If something releases 2 OH minus ions, say for example this barium hydroxide, then you have a diacidic base. Okay, so then look at an example calculation of pH for a base. Okay, so you got strong base here, its concentration here. We need the concentration of OH minus ion as against H plus ion for acids to start with, and then we need H plus anyway in the next step. So we have a strong base, so the concentration of the base is the concentration of the OH minus ions. So this is a simple step, because we have the concentration of the alkali. I'm just going to write that number here because that's going to be the same as this. Then H plus ion using Kw, the results that we've just seen in the previous page, right? The product of H plus ion and the OH minus ion is going to be 1 times 10 power minus 14, right? Now if you divide we have the concentration of the OH ion, right? So I'm going to write H plus ion times 0.025 equals 1 times 10 power minus 14. Rearrange this, divide both sides by this number, that gets cancelled, and then you get 0.025. You got the H plus ion concentration. I guess that you know what you can pretty much guess what's coming next. So once you have the H plus ion, you do the minus log of that value here, right? So now you have this. All you have to do is do pH. So to find the pH, you just have to do minus log of this value, 4 times 10 power minus 13, which is that value here, right? So you just got the hydrogen ion concentration and then put that in there, minus log of this gives you the pH of 12. That gives 12.4. Also missed the unit here, mole per dm cube. You don't have to write the units everywhere in your calculation steps, but at the end you have to think about the unit, when you have final result. Practice time now. Easy questions, right? Let me just have a look here to see anything else that you need to know before you can attempt these. I don't think there's anything here. So you have to just find the hydrogen ion concentration using water, the ionic product of water. I suppose you can do this. So you have to bear in mind H plus concentration OH minus concentration equals 1 times 10 power minus 14. Okay, so remember this value. Okay, so using that you can actually solve all of this, right? So you can work that out. That's easy. Pause the video, check the answers here. No, not yet. Okay, you got the warm questions, right? So do all of this. In this, mind you, you have this diacidic base. Okay, so you're going to work out the pH of this. So to work out the hydrogen ion concentration, you have this. They're all strong bases. You have only the concentration of this, so you have to work out the OH minus concentration. You have to multiply that by 2 because this is diacidic base, right? Okay, the other things are straightforward. Now you can pause the video, try these questions as practice. Try these as well. Really harder questions, right? By addition of water to 100 centimeters. So these are all involving dilution. Calculate the pH. So you're going to first work out the final concentration after the dilution. 100 centimeter cube of that concentration. So you're starting off with 25 centimeter cube. Adding water to 100. So initial volume, final volume, initial concentration. Addition of 25 centimeter cube to 100 centimeter cube. So be careful with this, right? It's not made up to 100. So you're just taking 100 centimeter cube of 0.1 concentration of mole per dm cube of this. You're just adding another 25. So the final volume will be 125. So be careful in the wording of this and use that in your calculation. I suppose you can do this. Pause, practice, time to check your answers. Pause and check. If you're on this, pause and check your answers. Pause and check. Check your answers for the practice questions. Really hot category. More answers here, right? So I hope you got all of that checked now. We're going to keep moving with this. Okay, I said we look at the relationship between pH and pKa. This is a relationship, and this is called Henderson-Hasselbalch's equation. pH is equal to pKa plus log of the conjugate base. So we can write like that, write the same thing in a slightly different way, like so, right here. Okay, pH equals this. That's the equation that we look at. That's the conjugate base, and here's the acid concentration. Now, when you actually, this is the original equation that we looked at. If you swap these around, this sign changes into a minus. Can you see that changes into a minus? But both are pretty much the same. Both are the same equation actually. But if you swap this denominator to the numerator and denominator, then you have the sign changes. So beware of this. Be careful with the use of this equation, right? The reason for using this is to easily see the connection between pKa and the pH, right? Now, this will be more useful when we actually look at buffers, right? It may not make a lot of sense here now because we now have the acid concentration and the alkaline concentration worked out for weak acids. We don't even have the A minus considered at all. So we look at these, come back to this pKa idea or this particular equation. It's worth actually making a note of this. We'll come back to this later on and you actually use this. That's it. This is part 1 and okay, you should be happy, but we are going to come back in part 2. We're going to just look at buffers, all right? So so make sure that you are ready for part 2, and then after that, part 3, we're going to be just looking through exam questions.